Hello! In this video, we'll analyze the performance of the single cycle processor. So now that we've built the single cycle processor, let's see how fast it can run a program. Recall that the program execution time depends on the number of instructions in the program, the average number of cycles it takes to run each instruction, and the number of seconds in the cycle. In other words, it's the number of instructions times the CPI times the cycle time. So we need to figure out the cycle time of our processor, and there's sometimes more than one possible cycle time. We'll have to actually look at the elements to figure out which one is the limiter. So I've labeled two possible cycle times in blue and gray on this figure. We're looking for the longest path, so the hardest thing, and the load word instruction seemed like the hardest thing because it uses the most different parts of the system. It uses the register file, the ALU, the data memory, and then writing back to the register file, as well as fetching an instruction. So the cycle starts when the program counter comes out of the PC register. We go into the instruction memory, and we've got to wait to read out the instruction. Then we fork, and we have a couple different paths. Let's start with the blue path, where we are accessing the register file. So we provide some bits from the instruction to the register file, and we wait to read out the data. Then that goes in as source A to the ALU. We read out that source, and that value goes to the ALU. We do a computation. We provide the result to the data memory and read out the answer that we're loading. That goes into the result multiplexer. We bring it around and need to write the value back into the register file, so the WD3 terminal holding result needs to set up before the end of the clock cycle. Another possible critical path is one involving the immediate. So for the immediate, once we have the instruction, that goes into the controller, and we need to compute IMM source to say what type of immediate it is. Bring that value down into the immediate extender, and based on that we get out our immediate. Takes some time to choose that second source in the source bmux, and then goes into the ALU. And then the rest of the path is the same. We still need to read data from the memory, go through the result mux, and write it back to the register file. So whichever of those two is longer may be the cycle limiter. So the critical path of the single cycle processor is the time through the program counter plus the time to access the instruction memory, plus the longer of the two of either reading from the register file or decoding the instruction, sign extending, and going through the source bmux. Then we have the time for the ALU, the time for loading from the data memory, the time for the result multiplexer, and the time to set up the register file. So the limiting paths are usually the memory, the ALU, and the register file. Those tend to be the hardest things to do. So if we assume that the register file read is longer than the other path, then our critical path is all of this stuff, or in other words, the time from the program counter to memories, the instruction and data, reading the register file, going through the ALU, the result mux, and then setting up to write the register file. Here's a table of component delays, and assuming these delays, we have 40 picoseconds for the program counter, 2 times 200 picoseconds for the instruction memory and data memory. We have 100 picoseconds to read the register file, 120 for the ALU, 30 for the result multiplexer, and 60 to set back up at the register file to write, and adding all these up, 400, 500, 620, 660, 690, 750. 750 picoseconds. So now suppose we're running a program that has 100 billion instructions in it. That's 10 to the 11th instructions times the single cycle processor, so by definition there's one cycle per instruction, times the cycle time is 750 times 10 to the minus 12th, and that is 75 seconds. So our single cycle processor takes 75 seconds to run our program.